Welcome to NPTEL course on power system protection. Today we will continue with distance link on multi-terminal lines. This lecture is on the issues with multi-terminal lines, the protection issues, and how the distance link performs in such a configurations we will see. Now, last lecture we discussed about two terminal lines having multiple circuits. We discuss on the double circuit line, otherwise called parallel line also, but that such a system can be also we will find with having more number of parallel lines, quad circuits, and so having 4 parallel lines or so. We discuss on the zero sequence mutual impedance aspect with further discussing on that perspective on different configurations in transmission system. This lecture is on multi-terminal lines. If you see this, we have a 3 terminal configurations here, but such terminals can be more in number also, but in power systems in the multi-terminal configurations 3 terminal lines are more common. In such a situation, it has a economical advantage, as at the tap point we do not need any substation or the associated equipment. So, whenever a load center or the a generating point comes out, instead of connecting this, say this center directly having a different line to the N bus, which requires right of way, and so this L bus can be connected to a nearby line and which can dispatch power to the N side or any other side. So, this advantage leads to the existence of the need of multi-terminal lines, but it has operational and also these protection setting issues. So, we will discuss on the protection perspective. Now, what happens when we have a source or a star grounded delta transformer connected here, then in any case a fault happens to be any of the 3 sections here, all the 3 sources participate in that fault. Say fault will be here, so this generator participates, so also this, and so also the N side generator participates in that fault. So, that leads to a different scenario on apparent impedance seen by the distance lane. So, the associated protection issues. Now, note here that anywhere in these 3 sections a fault happens to be there, then all the 3 breakers associated at all the 3 buses must trip, otherwise the fault will be fed from the on trip circuit breaker side. So, that is what the basic need of protection. We will see the problem and or the issues, and then we will go to the different setting perspective for distance relay. So, this is the 3 terminal line and we have the tap positions P, where a source is being connected to at bus L. We have M and N line we are observing the relay at R m. Similarly, you can consider the relay at L and N also. These line sections have their impedances P the tape point. So, impedance between M and P is ZMP, impedance between P and N is ZPF, F being a fall point here, ZPF plus ZFN, and impedance from P to N is ZLP. They have their associated positive sequence impedance, negative sequence impedance and zero sequence impedance for each line section. For easy assessment, we consider that each line section is having same conductor. Thereby, and the tower structure, thereby the per kilometer impedances remain same. Now, let us consider this distance relay at the R m distance relay at bus M. We consider first 3 phase fault in the line. Let us consider 3 phase fault at F. So, in the section P to N, and how this relay at M sees. Voltage at bus M will be this corresponding drop from here till P and from P to M. So, we say if we consider the positive sequence current, which the only component of current flows during the 3 phase fault. So, we say that the corresponding current in this part ZPF part, if you see from this side, current from bus M flows and also current from bus L flows. So, these two generators participate feeding current through this path. So, the common path is P to F, and from P to M for relay R m only the I m current flows. This I m current is the current through the relay R m, but from P to F the corresponding current becomes I m plus I L. The I L component of current is not associated with the relay R m. So, with that difference, if we see the drop from F to P from the 3 phase, so that becomes equals to I 1 m plus I 1 L current with the associated impedance Z 1 P F plus we have Z 1 M P plus I 1 M, Z 1 M P plus I 1 M. So, that is the voltage of V m for the 3 phase fault. But we know that the positive sequence voltage and current is same as the phase component of voltage and current also for each phase. The apparent impedance seen by relay R m for this 3 phase fault equals to V 1 m by I 1 m equals to V m by I m, as you know. So, that equals to, if we divide, consider this I 1 m here or the same as I m. So, that becomes equals to Z 1 m P plus Z 1 P F plus 1 plus I 1 L by I 1 m. We are dividing by I 1 m, but we have a term now I 1 L. But the fault point from the relay bus, the positive sequence impedance between these 2 points is Z 1 m P plus Z 1 P F. So, the actual positive sequence impedance up to the fault point from the relay bus is Z 1 m P plus Z 1 m, Z 1 m F, Z 1 P F. But what the relay will see now in this scenario, because of this I L current, we will see Z 1 m P plus Z 1 P F 1 plus I 1 L upon I 1 m. So, this ratio difference, the additional term Z 1 P F into I 1 L upon I 1 m is the additional component in the apparent impedance calculation. So, that is the difference we notice from the actual impedance, positive sequence impedance up to fault point versus the apparent impedance seen by the relay for the 3 phase fault case. Now, we will see for the same system, same fault point, we will see now the what happens for the phase A to ground fault, its analysis. We know for phase A to ground fault, the relay voltage VAM equals the VAMF equals to VAF equals to VA1F plus VA2F plus VA0F equals to 0. Now, you see here this VAM, the relay bus voltage during the line to ground fault will be available from this calculation related to this sequence component analysis. So, what we see here that we have these three components VA1M, VA2M, VA0M similar to what we have analyzed in earlier discussions also. So, if you see this VA1M, this is the corresponding sequence network for this system. If you see here, you can say that for this fault, for this relay, the corresponding current in the PF section is contributed by these two generators. So, they are in parallel. So, what we have done here, this is being fault point to the left, this is the section here common section from bus P, and then you can say that these are the two parallel parts contributed by the two sources, the sources at M and L, and then like this for the this is for positive sequence, this for negative sequence, this for 0 sequence, and this is the fault point. So, we connected for RF equals to 0 like this, and that you can say that is our the sequence network diagram for the phase A to ground fault. So, now to evaluate VAM, VA1F plus this drop is VA1M. So, what we see here that the corresponding VA1F plus I1M plus I1L Z1PF, two currents, this current plus this current, and from here to here it is only I1M Z1MP. So, this is what we have written VA1F plus I1M plus I1L Z1PF plus I1MP. So, this is for positive sequence. Similarly, for the negative sequence also the diagram is same. So, you add you can say that similar terms for the negative sequence component and also for 0 sequence component. This is being phase A to ground fault. So, all three components will be there. What we see as compared to the earlier two terminal derivation, that we add another current now for the Z1PF portions, the common portions where the both currents flow I1L, IA2L and I0 0 sequence, I0L the 0 sequence component, and they are associated impedance. Now, if we segregate the different components like we did for two terminal line, so we have I1M Z1MP plus Z1PF, that is this portion of impedance, positive sequence impedance. For I2M also negative sequence contributed with passing through the relay bus, this current for the line, this corresponding impedance negative sequence impedance plus 0 sequence impedance also I0M. Now, we have another three term associated with this I1L Z1PF, I2L Z2PF plus I0L Z0PF. Now, for these three term, this is same as what we have discussed earlier. So, we can do the corresponding 0 sequence compensation factor aspect, and that will lead to our you can say that Z apparent calculation perspective. So, Z1MP plus Z1PF. So, these are the three components of current sequence component. So, so to get that you can say that we subtract this one, because we have considered here Z1MP plus Z1PF I0M. So, subtract here and add the same component Z0MP plus Z0PF I0M, and then we have Z1PF plus this additional term will be there. So, for this also we did similar things, and therefore, what we did here that we add Z1PF plus I0L plus I0 Z0F these two terms. So, we have added these two terms addition to what we have found here. This leads to Z1MP plus Z1PF IM plus K0 IM I0 M plus Z1PF plus IL K0 I0 L. Note, we have already talked about the 0 sequence compensation factor, and that is what Z0 minus Z1 divided by Z1 of the line, and we have considered that all sections are having similar per kilometer impedances for all sequences. So, this if we substitute this, then we will get the corresponding relations to be like this. And if you move further, then the Vm expression we got this in terms of this k naught. Now, if we calculate the Z apparent for this relay for this fault phase A to ground fault, Vm upon I m plus k naught I n naught m. So, that if we divide by this term, so this becomes equals to Z 1 m p plus Z 1 p f. This is the usual term we should get Z 1 m p plus Z 1 p f up to this point, plus an additional term Z 1 p f plus I L k naught I n naught L plus I upon I m plus k naught I naught m. So, this we are dividing this, you can say that by this perspective, this one. So, thereby you can say that because we have additional term in terms of I A L and k naught I naught L. So, this term is remaining this one, and the Z 1 p f is for this portion, the common portion for the currents I L and I M. So, this leads to like the case of 3 phase fault we saw. Now, only that additional term the zero sequence compensation factor is coming here, and for that the two zero sequence current are also the associated are that the corresponding zero sequence current at bus L also what is being flowing coincident in this circuit. So, that is also coming to picture in the Z apparent calculation. So, two situations, suppose at one instant there is no infeed, this source is out from operational perspective, then there will be no I L current flowing this. In that case, this component will be 0, this part. So, therefore, only these two components will be there. So, Z apparent at that time will be Z 1 m p plus Z 1 p f for the fault F, phase A to ground fault at F. So, this will be this. Now, suppose another case with L source present, and let us say consider its contribution is 50% what the corresponding relay current is being there at that time. So, if we consider this ratio to be 50% 0.5, then if you substitute this in our derivation here, if this becomes 0.5, so then this Z 1 p f plus 0.5 Z 1 p f gives us 1.5 Z 1 p f as compared to when the source L is not available. So, as compared to two terminal equations and related Z apparent calculation, we saw that you can say that this impedance is now in the presence of the source at L, that we call infeed current contribution. That infeed current you can say that is 50%, then the corresponding apparent impedance becomes this. So, as compared to this apparent impedance, this will be higher, that means that the relay at this will be an underage issue, we will find an underage issue for this kind of infeed you can say that situation with a distance relay protection perspective. In moving further, we saw that you can say that when there is a tape current infeed, the Z apparent seen by the relay is greater than the actual Z positive sequence impedance up to the fault point from the earlier analysis we saw. Now, if we say suppose the zone 1 setting is of 80% for the of the line M L or so, relay may not operate for many faults. So, what will happen here, if we consider this line M n to be much longer, and then if we go for the zone 1 setting in terms of line from M to L, the shortest distance, then many fault points in the system because of this underage issue will not be detected in the zone 1. That means that if a zone 1 fault happens to be there towards the reach and with the infeed condition, then the zone 1 will not detect it. It means that will be detected by the other like zone 2 or zone 3. So, if zone 2 or zone 3 they detect, then it will be a delayed decision. So, that is one issue, and furthermore, if you like to, you can say that extend this zone 1 to further like 90%, 95% or beyond that to address this infeed, then when this infeed is not there, then that may consider go beyond this line section M n, and that may interfere to the interfere to the corresponding protections at bus n. So, which is also not desirable from the system security perspective. So, based on these above observations, we say that there are some guidelines for the protections for the multi-terminal lines, simple guidelines. The zone 1 setting should be decided without considering infeeds. From the above discussions, it is being a general recommendation is that zone 1 setting should be as usual without considering the infeed. So, when we are considering the R m, then we do not consider the infeed of I L for the zone 1 setting. Zone 2 and zone 3 settings need the consideration of the infeeds. Zone 2 and zone 3 settings need the contribution of the infeed settings. So, now we will go you can say that how that guidelines are being applied for transmission system having multi-terminals configuration. So, we have considered a system like this, the corresponding T point or the tap point is P, one section here, the infeed section from L to P, and then the another section from P to N. Now, for zone 3 setting, we have considered another section from N to K in an interconnected power system. But you see here you can say that this is a multi-terminal line, and so from N also for fault here inside these 3 terminals, 3 sections, from N side also current can flow, from L side also, and from also M side. So, the impedance as assigned PD sequence impedances available to us is in terms of 2 plus J 20, 4 plus J 40 and 3 plus J 30 ohms, and we have another section N K having 4 plus J 40 ohm. This is for a simple example. The task is that to set the 3 zones for the relay R m, which is someone can extend you can say that for the relay at L and N also. We will consider maximum the infeed amount is for this case for this relay is I L upon I m equals to 50% 0.5. Now, first we will consider zone 1. So, for zone 1 as in the guideline we will consider no infeed issue and then we will go ahead. Now, this is set equal to 80% of the smaller of the 2 impedances between buses M and N, M and N and M and L. So, what will say that from this relay whichever length becomes smaller and 80% of that will be for zone 1 setting, but without any infeed term which we have seen in the apparent impedance equation. So, for zone 1 setting we say if you see this from this for this relay from the tap point, this path is having smaller impedance. So, our zone 1 setting will be 80% of 4 plus J 40 plus 2 plus J 20, 80% of that becomes equals to 4.8 plus J 48 ohm. So, from P the zone 1 will see this impedance minus this you consider this section. So, only 0.8 plus J 8 additional impedance up to that portion you consider from this side to this side or this side to this side it will able to see. For 3 phase fault at the reach, for 3 phase fault at the reach, let us say at this reach, this is the reach you can say that it for this setting. When I L is providing a 50% compared to this I M side current, then as we have calculated for the 3 phase calculations that this will be 4 plus J 40, 1.5 of this portion, which portion? This section. So, 1.5 into 0.8 J 8 at the reach point. So, that becomes equals to 5.2 plus J 52 ohm. So, if we see that this is the setting of the up to reach for the 80%, but the at the same reach point at 80% physical distance, the corresponding 3 phase fault gives you consider 5.2 plus J 52. Here we have not considered any infeed, here by considering the infeed as in the 3 phase calculations, we saw that the corresponding impedance will be this much. So, this is higher than this, it means that this is will lead to underage problem. Now, next we will go for consider the zone 2 setting. The zone 2 setting is 120% or so, we know for the 2 terminal line of longer of the 2 impedances. In this case multi-terminal line, it will be 120% of the longer of the 2 impedances between buses M and N and M and L. So, we have from this relay bus we will have 2 sections 1 and 2 and the other one you can say that is this one. So, whichever is the longer out of that 120% with the consideration of the in feed. So, for this what we will do, the zone 2 setting equals to 120%. So, this is 1.2 4 plus j 40 fine, and then we have you can say that longer is this part. So, in feed will be there from this side. So, we will consider this in feed. So, in the Z apparent impedance if you remember that becomes equals to the in feed part 1.5 now of 3 plus j 30, and then you can say that 120% of that one. So, 1.2 4 plus j 40 this part and with in feed considerations 1.5 into 3 j 30. So, this becomes equals to 10.2 plus j 102 ohm for the zone 2 setting. Note that in zone 2 setting relay at RM must address this part and also this part completely. So, that no fault in these two including these 2 sections can remain unidentified, otherwise it will be a protection problem from the primary protection problem, and the fault will continue you can say that from either from the M bus side for this design. Now, we will go for the zone 3 setting for the system. In zone 3 setting similar to the zone 2, what you do is that the apparent impedance of the Mn in feed is 4 plus j 40 plus 1.5 3 plus j 30 up to this N section. So, this impedance plus the considering the in feed 1.5 3 plus j 30 for zone 3 also will go for the higher length distance. So, this becomes 8.5 plus j 85. Now, for this section also, because zone 3 has to back up section N k also. So, any fault here also the corresponding in feed current will flow. So, therefore, you can say that we will consider that the corresponding settings for you can say that 8.5 j 85 up to this N point from N k from N to k 4 plus j 40 1.5 times with consideration of in feed. So, that gives you can say that and 120% of that. So, if you get that you can say that becomes 17.4 plus j 170 ohm 174 ohm. So, that leads to situation that we say the zone 3 should take care this portion as well as this portion and should ensure that no fault is unidentified in this one. However, zone 3 is a delayed decision process. Now, we will take a case example, simulated example how the zone 1 performs in a multi-terminal line in a 230 kV system we have considered, the way we have presented for a 3 terminal line. So, it has a 50 kilometer here, 70 kilometer this section and we have a 300 kilometer long line from P to N section. The zero sequence and the positive sequence per kilometer impedances are available to us. Now, we will see how the zone 1 setting will be there and then we will assess how good is the zone 1 setting. So, the zone 1 setting for that as we have seen the guidelines and simple calculations earlier, for RM relay the zone 1 setting will be 80% we have considered. So, this is 70 kilometer plus 50 kilometer, shortest this 70 plus 50, this is the shortest path. So, 70 plus 50 120 kilometer into the per kilometer positive sequence impedance. So, N into 0.8 that 80%. So, that gives us 1.92 plus j 27.523 ohm. So, this corresponds to EPC 70 plus 50 120 kilometer, physical distance 80% of that is 96 kilometer. Similarly, for the zone 1 setting for L for Rn not L for Rn with this in feed for Rn the zone 1 setting becomes 0.8 plus 300 plus 50 minimum distance into the corresponding Z 1, that gives us 5.6 plus j 80.276 ohm. Now, we will see for a phase A to ground fault in the system, how the corresponding zone 1 setting is good enough or not. For this, in the system, a phase A to ground fault is created at 85 km from bus M, which happens to be in zone 1. As we have seen this setting, the zone 1 covers physical distance of 96 km. So, therefore, this fault at F, which is only 15 km from P, this part is 70 km, happens to be in zone 1 fault for R m. By creating the phase A to ground fault, the corresponding phasor voltage and the phasor currents are noted here. So, we see here the corresponding phase A current is much higher than the other phases. Now, there will be infeed from this side during that moment. The K naught for this situation is available from the Z naught and Z 1, Z naught minus Z 1 upon Z 1. This I 0, the resequence current for this situation is obtained from IABIC. So, we apply the normal Z apparent equals to V A upon I plus K naught I naught, and we got the impedance to be 2.13 J 29.84 ohm. Whereas, our zone 1 setting for the 80% of M to P plus P to L, because P to L is the minimum distance from P side. So, that gives you 1.92 plus J 27.523 ohm. Now, you see here, even though we have simulated at 85 km, which happens to be zone 1, the fault is seen outside zone 1. So, that is what we mentioned earlier also, is an issue of underreach for the zone 1 operation of distance relay. Now, we will see that the apparent impedance which we have derived for the phase A to ground fault, that can be validated if you know the corresponding bus L, the infeed currents which we have noted here, 3 phases current at bus L during that same fault, corresponding zero sequence component of current. So, we have already derived this for the phase A to ground fault, Z 1 M P plus Z 1 P F plus Z 1 P F into I L K naught I A naught L upon I M plus K naught I naught. So, in this relation, if we substitute this current, then and the different impedances, then we got the corresponding impedance to be 2.12 J 29.77 ohm, and that is what we got from the Z apparent impedance calculation V A upon I plus K naught I naught. So, this shows that our Z apparent impedance calculation is correct. So, what we found from this example is that for this case, that the zone 1 underreaches because of infeed issue, and we cannot extend this zone 1 to larger also, because when the infeed is not there, it may create problem to for the other bus relays and so in the zone 1 domain. So, in overall, we see that multi-terminal lines is a challenge for protection, particularly for distance relay we saw here, even with through examples also. More infeed, more underreach. Further, the position of this infeed is also a factor in the amount of underreach issue, particularly for zone 1. Of course, zone 2 and zone 3 also have also underreach issue. While settings for different zone 2 and zone 3 particular, the maximum infeed should be considered, but note that there at an instant infeed may not be there, even that time also the protection scheme should function properly. So, in overall we saw that the challenges are more as compared to the 2 terminal line case for this configuration of transmission system of 3 terminal lines. Thank you.